Hello, everyone.
Hello.
Second last course already, I realized. Thursday is a day off. So it's a holiday, some kind of holiday. And so we have a course on Tuesdays, next Tuesdays, and then the following Thursdays, the seminar starts. So I wanted to advertise. I thought it'd be fun to, I guess, mark the end of the course with some event. We could go for a drink if you want at Kurma on Tuesday afternoon. Right after the course, right after next course Tuesday. It's going to be 4:30. Sounds like a good plan to have a 5 à 7. If you guys want.
Next week?
Bad choice.
Bad choice? Yes. Oh no, I'm so sorry. Well, come later. Just come after. I already told Stefan, so he's probably going to come.
Next week?
Next week,
1 week.
Tuesday.
I have an Italian spoken final exam
Oh,
during that time, so I might come later.
good luck.
Wait, so Stefan comes and I have to take the exercisation. Okay.
Nothing says we're going to be done by 6:30.
Yes.
That's why I said you can come after.
Yes.
Yeah. It's a proposal. Do whatever you want with it. That's one thing. Now the other thing, today we're muscling through probably the larger theoretical result of this course. So I'll try and go through at a somewhat good pace. I would like to, by next Tuesday, to get at, the main idea of the coding theorem and the main result. And worst case, we leave some details for either problem sheets or for your own problems, your own situation to solve by yourself. I don't really like, or I might just send notes. I don't know. We'll see how we do it. But I might not be super picky on details because I want to get to final destination in time. So that's just a disclaimer. Are there questions before we start? Okay, let's go. I started with a reminder of P of x. We met P of x, which was the universal probability. Which I think I qualified like as Solomonov's great idea. Sum over all p's such that u of p builds x 2 to the minus length of p. We're summing over all programs that compute x 2 to the minus the length of that program. This is the idea of our monkey in front of the universal computer. Now note that this sum has an obvious term, which is 2 to the minus x star, length of x star, right? Because one way to produce x is via x star, the shortest program for x. But it's going to have various other terms. In fact, it's going to have infinitely many other terms. 2 to the minus length of p1 plus 2 to the minus length of p2 plus where p1 and p2 are other programs that compute x. There's many other terms in that sum. This is 2 to the minus k of x, isn't it? Length of x star is k of x. I see some of you, you might have seen that I've shared my notes for the whole semester. Be free to improve them, please do. If you reread it, please go ahead. Okay, that is one thing. So clearly, P of x is greater than 2 to the minus k of x. That's a relationship that we have between P of x and k of x. The relationship between P of x and k of x is the goal of the coding theorem. We found an obvious relationship. P of x is larger than 2 to the minus k of x, Because 2 to the minus k of x is just one term in the sum.
Be larger or equal in case there's only one. Oh no, there's not always only. There's always more than one program.
There's it. As soon as you've got one program, you've got infinitely many programs. So it's clearly larger, strictly larger.
Yeah. Okay.
Question is, how much larger? How much larger than 2 to the minus k of x can p of x be? And I'm going to come up with something pretty informal. So for some x of length 50, I'm coming up just like that. I made up the number 50. There might be three programs of length k of x, which is the shortest possible length for programs that compute x, and 4 programs of length k of x plus 1, which is the next length that is possible for programs to compute x. There might be 4 of them. So for that x, well, what have we got? P of x will be larger or equal to 3 times 2 to the minus k of x, because I have 3 programs of the shortest length k of x, plus 4 times 2 to the minus k of x plus 1, plus other terms. Actually, if I put, I'll just neglect the other terms because I've already put larger or equal to. So I'm only considering the contributions of the shortest programs. I suppose I have 3 of them, and the next length I have 4 of them, which is basically equal to, I can use the 2 to the minus 1 here and factor it out, which gives me 1/2. So that 4 becomes a 2, and 2 plus 3 is 5. 5 times 2 to the minus k of x. Okay, these two things together, they sum up to 5 times 2 to the minus k of x. Again, because 2 to the minus 1 that I put in evidence meets the 4 and becomes a 2. And then I factor out 2 to the minus k of x. I got 5. So in that case, I would have some x of length 50, in which p of x would be 5 times, at least 5 times greater than 2 to the minus k of x. I'm making it up. I guess the question becomes interesting if we investigate what happens if we consider larger and larger strings. Can that constant grow unboundedly? You know, if I start considering programs of strings of length 5,000 bits, you know, can I have 300 shortest programs and 400 programs of the next length so that this constant becomes 500 and so on? So can this constant grow larger? Let me ask the question. But as the length of the considered strings grows, it might be expected that the number that multiplicatively relates p of x to 2 to the minus k of x grows unboundedly. Note that it's just actually one way to have such an unbounded growth between this quantity and that quantity would be to have a number of shortest programs which grows unboundedly. You know, if for strings of length n, there exists, for each n, there exists a string of length n such that the number of shortest program that it has is a growing function of n, well then, I will not have a fixed constant that relates 2 to the minus k of x with p of x for all x. Because for that string, for this family of strings, it grows unboundedly. The coding theorem shows that this is not the case. There exists a constant c such that for all strings two to the minus k of x is, as we've seen, is always going to be a smaller quantity than p of x. That's not a surprise, that's easy to show, we've already done it. But smaller or equal than c times 2 to the minus k of x. There exists a constant c such that for all x. So that constant does not depend on x. And so my speculation about, you know, what's the number that relates this to this, as the length of x grows, it might be an unbounded number. Well, the answer is no, it's a fixed constant. Or another way to put this relation is to write it this way. Take the log on each side. When I take the log, I'm not changing the side of the inequalities because the log is a monotonic function. So I would have minus k of x smaller than p of x smaller than c times minus log of, well, let me do it. I'll do it 2 steps. Taking the log on each side, I have minus k of x smaller than log p of x smaller or equal to log of this. What's log of this? It's log of constant plus minus k of x. It's the log of a product. When you take the log of a product, it's the log of this person plus the log of that person. For a reason, they became people. And then the log of that person is minus k of x. It's annoying because they're all negative quantities. In fact, no, this is a positive constant, but let me just rewrite it positively. So I multiply by minus 1, and by multiplying by minus 1, I have to switch the signs of the equalities.
Minus log of c.
Thank you. In other words, if we wanted to look at as a measure of complexity, not the length of the shortest program, but Solomonov's proposal. Let's look at all ways in which this string can be generated, and then take the log of it, or minus the log of it. We would have come up with a notion which is O of 1 close to K of x. Basically the same notion. Just before stating the coding theorem, let me just define something. The conditional universal probability I will write it P of x given y. X and y are strings. And it's equal to, well, P of x is there. So what could be P of x given y? The universal computer has access to y as an auxiliary string to produce x. Sum over all p such that u of p comma y equals x 2 to the minus length of p. P is whatever sits on the input tape, which is the one-way only, bit only tape. Y is the work tape / auxiliary tape. I prefer to have the conditional version of the universal probability, because I will state the coding theorem in its conditional version, which is slightly stronger. Actually, I'll write up there. For all strings x and y, k of x given y is equal to minus the log of p of x given y plus an error term, which is a constant independent of x and y. Let me go back here, no, here. So that's basically what it says here, but in the unconditional case. Here there's no y's. And I'm saying that, yeah, this quantity here, minus log p of x, is equal to k of x up to some error term. That is a constant. Are there questions before we move on? No? Okay.
I want to make sure if I understand the blue conjecture correctly. You're saying the P of x does not contain mostly complications of the shortest program.
It does not contain
Mostly complications of the shortest program. So it sounds like they're like the short program and just add stuff on top, and because of that, you can just take away the shortest program and leave the noise.
Okay, once you have the shortest program for x, you can add complications to make more programs. of x. Like, so they do contribute in the P of x. But what the coding theorem says is that they do not contribute in a way that affects significantly log of P of x. So they will add contributions which basically converge below a constant. Right? Like that constant is if you see it this way, it exists. It depends on the reference, on the universal Turing machine we're using in the setup, but it's a fixed constant. I don't know, like 1000. Or it might be shorter. We'll see from the proof how big it is. That's actually biggish. The program is not so simple.
So it's like the compiler constant.
But it's a constant.
It's like the compiler constant, but for this setting.
Yeah. Nah. How do we prove that? I'll connect. Let me just move on a bit, and I'll connect back to your comment. Other questions before we move on?
Isn't blue untrue because we know P of x is lesser than omega? Because we know because P of x is defined as x halts, right? Like, I mean, it halts and outputs x. So P of x is always lesser than equal to omega. So we know that it can't grow unboundedly, at least. Like, maybe we can't get a specific relationship, but we know that it can't grow super much.
It could still grow unboundedly, but yet this thing would be smaller in a way that, you know, you can still have a non-trivial increasing function of x, or of length of x here, together with that, in a way that it's still smaller than 1. Because invoking that P of x is smaller than omega, you're just saying P of x is smaller than 1. But we're looking at the asymptotic behavior. It could still be, there are plenty of possible functions which will still remain that quantity smaller than 1. Because you're right, an obvious bound for P of x is 1. Because of omega, or because of prefix freeness, ultimately. But yeah, it doesn't rule out the fact that this can still grow unboundedly. Okay, I stated the proof in the conditional case. Now I'm going to prove it as if we set y equals epsilon, just to make our life easier. Otherwise, the notation just gets heavy. But every time you see, oh, we invoke a Turing machine that does blah, 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 it would do the same thing if it has y on its auxiliary tape. So another way to say it, like, let me just first write the proof. It's going to be your first exposition to this proof. Do it without y. And if you want at home, reread the proof and check what happens if we have y. You're going to notice that nothing changes. Y just sits on the auxiliary tape. But it makes my life just a little easier in terms of presentation, and we don't need to care about y. Proof. We need to show that k of x is smaller or equal to minus log p of x plus O of 1. Why we need to show that? Well, remember from that equation we already had one side. We had this side. So I'll put in green the easy side. This was the easy side, the easy side. This was the easy side. It flipped because we took minus on each side. The non-trivial result, which I started to state here, was that equation. That P of x is bounded by a constant times 2 to the minus k of x. And so taking the log, it gives this. Taking minus side on each side, it gives this equation. Now this equation, that's a negative constant, so let me put it on the other side. It really means that k of x is smaller or equal to minus log p of x plus the constant, which was log c, but let me just say plus O of 1. Right. That's what we need to show. Okay, so the green was already done from the introduction. The hard side to show in that relationship is this one. And so I rewrote it here. So Vol, I said I'd come back to you. You said does the O of 1 relates to the precise decompiler we're using, or the precise universal machine we're using? It implicitly depends. Like K is defined with respect to some universal machine, and P is defined with respect to some universal machine. But this O of 1 we're going to get from a usual argument, which looks like we're going to come up with one program to produce X that has size minus log P of X. Or one computation, I should say, to produce X, which has size minus log P of X. And then the universal computer can simulate that computation with a constant overhead. I'm going to be writing this now. We shall do this by exhibiting a Turing machine T that computes each X from an input AL. It's going to be AL. We'll see why. Of length minus floor of log minus floor of log P of X plus 1. So we're going to come up with a Turing machine, which is going to take as an input AL, some input for that Turing machine. That AL has the desired length, basically minus log P of X. The plus 1. It's not going to change much. And then what are we going to do? We're going to invoke the fact that the universal computer can simulate that Turing machine with a constant size prefix on that input. And that input will have the length log P of X, minus log P of X. So since you can simulate that machine, it provides a program of length minus log P of X plus O of 1. The O of 1 absorbs, okay, that 1, but it mostly absorbs the constant cost for U to simulate T. To compute X, and thus, as usual, we will have found one way for you to compute X will be to simulate T on input AL. This will have total length that, and thus the shortest program is going to have a shorter length, which is going to explain that K of X is smaller or equal than that way of getting to x. And thus the shortest program for x has a length no greater Are there questions relating that relates to the idea?
Just you said, I think, flaw of log, but you wrote seal of log. Which log p of x? Which is it? Like length of minus seal log of p of x.
Yeah, that's the ceiling.
Yeah.
That's the ceiling.
Yeah.
I said floor?
Yeah.
Okay, sorry. Yeah, sorry. In fact, once I rewrite it here, I can remove this one if you want, because it's absorbed in the O of 1. Here, that's just being precise. We will see that AL will have a precise length minus ceiling of log p of x plus 1. And then U simulates T, and we get a program for U which has length. That's the cost of the simulation of T. It's constant. And that's the size of the input of T, which grows with x. Questions? So just to make sure, we're proving this, but what would it be like if we would have given y and given y? Well, it's the same. We're exhibiting a Turing machine T, which have on his auxiliary tape the string y is sitting there, but I didn't want to write those down. And then it would come up with an input of length. Well, we have given y here. And yeah, the proof carries true, so I'm not going to comment anymore on it, but you can redo it and verify that it works if y sits there as not just a spectator. It enhances the possibilities for the computation, but it doesn't change the gist of the argument. More questions? Okay, what's T? What does T do? I'm going to be writing a program here. T. A good start is always to run all programs. Dovetail fashion. When the jth program halts, jth in the dovetail order. What do we do? Add this P, J, X, J, S of XJ, and AJ. Okay, 4 pieces of information. We'll process them to a list of quadruples. where the first one, PJ, is probably the most straightforward one, is the jth program that has halted. Or is the program that halted. Just to make sure you get the vibe, we're dovetailing all programs. That means we have a counter, let's call it T, I think I won't be using T. Set T equals to 1, run all programs of length shorter or equal to T for T steps. Increase T. Eventually I have a first program that halt. I'm gonna write a quadruple in a list, my first quadruple. P1, X1, S of X1, and A1. I'm gonna be writing that to a list. After I wrote it down, I keep going with my dovetailing. And I keep running all programs. Eventually,
Wait. You said 1, so the ordering that we're putting them in, J is an ordering of the order in which they halted?
yeah, in the dovetail order.
Okay, so that could be X27,
Yes.
27th program in the list, but it's the first one that halted.
Yes.
So that becomes J equals 1.
Yeah.
Okay.
I cannot hope to get my programs to halt in alphabetic order or in lexicographic order.
Yeah.
But they can halt in speed. The fastest one will halt the first and then so on. That's what we do when we dovetail programs. We get the shallowest computations or the fastest computations to give us an output first. So the first program has halted. I've wrote it down in my quadruple P1, X1, S of X1, and A1 in the list. And then I keep going with the dovetailing. Eventually I've got a second program that halt. I write down a second quadruple to the list, and I go back to the dovetailing, and so on. So I just wrote down a generic step. The jth program halts, and we add Pj, Xj, S of Xj, Aj to a list of quadruple. Pj is, well, the program that has halted. Xj is, what would be Xj?
Output.
The output. We usually use X to characterize the output. Xj is equal U of Pj is the output. Now S of Xj. It's going to be the lower semi-computation of P of Xj. Let me write it down. It's the sum for all I smaller or equal to j, such that xi equals xj of 2 to the minus length of pi. That's in math. Now I write it in English, and then we comment. Is the current value of the lower semi-computation of P of xj. Right. So what's the sum saying? Suppose j is equal to 17. We've had 17 programs that have halted. And suppose that xj is the string 0, 1, 1. Well, I'm going to look previously. Have I had other programs that have produced 0, 1, 1? Like other xi from I ranging from 1 to 17, such that I've already produced 0, 1, 1 maybe. And I'm going to add 2 to the minus the length of all those programs. So I'm lower semi-computing P of xj. Because P of x, as j will go to infinity and my running time will go to infinity, I'm going to add all the contributions of a given x, which happens to be xj here.
So it depends on all previous programs we found.
Yes, exactly. Yeah. So obviously for the first quadruple, this is just going to be 2 to the minus the length of the program I've just found. But eventually, as I keep having more programs that have halted, Sj remembers the previous value. It goes like, oh, cool, another program for 0, 1, 1. I'll go back in my list. My past proxy, my past value for the lower semi-computation of P of 0, 1, 1 was blah, blah, blah. And now I add 2 to the minus the length of the program that just generated it. So I'm coming from below to P of x. I will do an example, but let me first finish like what's AJ and stuff, so we can consolidate the proof via the example. What's AJ? AJ is the empty set or whatever symbol that means forget about it. If the position of the leading one in the binary expansion of S of xj has not changed. And if it has changed, AJ is the address of the first available of the, well, I made complicated sentences, of the lexicographically, it's just a line. Of the lexicographically first available node in the binary tree at depth ceiling of minus log S of xj plus 1. Okay, that's it. I stopped writing, but I'll help you process it.
That shouldn't be outside of the ceiling.
Why should?
It doesn't matter.
Oh, he's asking the minus should or should not be inside the ceiling.
It would bother. Why not? I'm just scared that otherwise it becomes a floor or something. I have some identities for. We're gonna be playing with it and seeing why. Okay, let me help you. So when AJ is not the empty set, which means that when we're lower semi-computing S of xj, eventually the leading digit, the leading bit changes. That's our bell to say, okay, we're gonna give some non-trivial aj. And the idea is to put xj, the output, to some node in the prefix tree, in the binary tree of strings. And we'll put it at the right depth. So at some depth, which, by the way, this relates to what is the position of the leading one in Sj. We will see why. And so we associate xj to a node in the tree. There's a break to take. And I guess I would like you to be more fresh, because to properly explain what is AJ with my example, I would need another 10-15 minutes. So let's call it a break here. Try to figure it out by yourself. What would it mean? And then I'll help you out with an example, which go like, oh, okay, I see what it is. It's not that like dark magic. It's just it helps to have something to grasp on. So let's reconvene at past. Okay, I'm still assuming that you have not understood AJ, but yet you have understood the idea of S of xj. In any case, the example will make both of them clearer. Let me, just before the example, do a bit more of meat around AJ. When AJ is not the empty set, the idea is to allocate the string xj to the node aj. Then to preserve a prefix-free tree, when a node is allocated, all its descendant branches are removed. Okay, example. Suppose that our x is equal to 11011. What are we doing? Well, we're running all programs dovetail fashion, and when some program halt, we do something. So there's something we're going to be doing is going to be writing down a quadruple. So this is going to be I and PI XI S of xi AI. Okay, and I equals 1, 2, 3, 4, 5, and so on. So I is labeling my AIT program that is halting. So when I'm dovetailing all programs, and then I find that, oh, I've got a first program that's halting. And that program is the program 1100. For example, as Will noticed, it's not necessarily the shortest program that's going to halt first. It's some program which halt first. In my example, it's 1100. And it happens that it produces the output 01, just like that. So it's not producing the X I'm looking for, but too bad. It's producing some other output. We write it down. Now, what's my first proxy for P of 01?
It's 4.
4? It's 2 to the minus 4.
To the minus 4, yes.
Yes. Right? Like, because P of 01, by definition, is the sum over all programs such that U of P equals 01, 2 to the minus the length of that program. I'm summing over an infinite number of programs. Now I've got a first program, which tells me, yeah, that's a program for 01. Its length is 4, so I'm going to contribute 2 to the minus 4. I'm really lower semi-computing this quantity. You know, there's an infinite number of terms, but I'm going to get them all when I goes to infinity. Now I got a first term. I write down 2 to the minus 4. Just to make sure people understand, 4 is because the length of that program is 4. I need to sum 2 to the minus the length of the programs. Now what's AJ? Okay, let's unravel this thing here. It's going to be the empty set if the position of the leading one in the binary expansion of S of xj, so S of 01, has not changed. Well, it has changed because, you know, prior to having it, my proxy was 0. This is 0, 0, 0, 0, 0. And then, wow, I have a first non-trivial contribution to a proxy of P of 01. And so my leading one has changed. And so AJ is going to be the address of the lexicographically first available node in the binary tree at some depth. Whoa, all right. Now what's the depth? Let's compute this depth. I have S of x1 is 2 to the minus 4. So, okay, S of x1 is equal to 2 to the minus 4. What is this depth? Well, first I need to take minus the log. Minus log of S of x1 is 4. You take the log, that's minus 4. You take minus, it's 4. And then I take the ceiling. In this case, it doesn't matter. It remains 4. And then I take plus 1. So let me just say, okay, I'm going to do plus 1 equals 5. So I need to look for the first available node at depth 5. Well, so far I've assigned no nodes, so they're all available. Therefore, this is going to be my binary tree. The upper path is the 0. And in lexicographical order, 0 comes first. Therefore, I'm going to run into my things. Okay, that's depth 1. Depth 2, 3, 4, 5. That's the node I'm going to select to label. I'm going to assign 0, 1 to that node. And what's the address of that node? Well, 0, 0, 0, 0, 0 is the address of the node. Okay, so it is at depth 5 because I have to make 5 choices. This is what my algorithms tell me. We're going to see why there's a plus 1 and so on. Don't worry. And I'm basically The idea is I'm going to assign the code word x1 at that depth. Yeah, so the address of the node, AI, is full of zeros. Questions so far? Because I want to have it, I will want to build a prefix tree. So I cut all the branches here. That's what I wrote in that remark. I will not allocate any more nodes here. But this branch is still alive if I need it. And obviously all these branches are still alive if I need them. So let's continue. I'm still in my example. We only had one program that halted. Now we run again, we keep dovetailing all programs, and we find that that one halts. 0, 0, 1, 1, 0. Why not? That's a halting program, apparently. And its output is 1, 1, 0, 1, 1. Oh, cool. That's the string we're looking to compute or to produce. So what's the first proxy for the lower semi-computation of our string x? Well, again, it's the first program that produces that string that has halted. So it's going to be 2 to the minus 5. And same trick again, but here we would get 6. Minus the log gives me 5. Ceiling changes nothing. Plus 1 gives me 6. So I'm looking to assign an address of 6-bit.
0, 0, 0, 0,
1, 0.
0.
Yes, correct. Yeah, there we go. The lexicographically first available node at depth 6. This was depth 5. Now I need to go deeper, depth 6. But I cannot go here because I've cut the branches. You know, I'm not going to go to 0, 0, 0, 0, 0. 6 zeros. Right? It's the whole idea of having a prefix tree. Well, otherwise this code word would be a prefix of the other code word. So I'll go downstairs and then upstairs again. And the path is going to be A2. But the code word that I assign here is going to be X2. Well, X, so 1, 0, 1, 1, 0. By the way, in my construction, I didn't say that we assign X to nodes, but that's like an interpretation for you. You can think that we're assigning the outputs to the nodes. But what matters is my quadruples. In my quadruples, what I have to assign here, it's a 6-bit string, and it's going to be 0, 0, 0, 0, 1, 0. It is the lexicographically first available node at depth 6. Now I cut all the branches here, but this branch is still alive, that branch was still alive, and so on. Questions? We had 2 programs that so far halted in the example. Each of them has happened to change the leading bit of the proxy for the lower semi-computation. So in which case I had to assign some AJ. I keep going. The third program that halts is 0, 0, 0. It produces the output 1. That's again a new output. So my proxy for P of 1 is going to be 2 to the minus 3. I'm looking for, therefore I'm going to assign a non-trivial address. The first lexicographically available string at depth 4.
3 zeros and a 1.
Yes, 0, 0, 0, and a 1. Correct. I could not do 0, 0, 0, 0. That's not available. It has to be a terminating node. Otherwise, I'm building a prefix out of my code words would not be prefix free. Actually, my pathways. So I'm assigning 1 here. There you go. And yeah, I did assign something because again I had a non-trivial first digit in the lower semi-computation of P of 1. Okay, now something different happens for the case 4. I've got some program that halt. It's 0, 1, 1, 1, 0, 1. It's a 6-bit long program, and its output is, again, 1, 1, 0, 1, 1. It's our x. Now, what's the new proxy for S of x4?
2 to the minus 5 plus minus 6.
Yes, there you go. 2 to the minus 5 plus 2 to the minus 6.
It's 57.
Yes, S of x2 was 0.00001. There was a 1 at the 5th position. Now S of x4 is 0.000011. This one is for 2 to the minus 5. This one is for 2 to the minus 6. I am not changing the leading bit in my proxy for the lower semi-computation of P of x. Therefore, I am not going to assign an address. I'm not going to assign any node. The basic idea here of why am I skipping this one is that I don't need it. My goal will be to reconstruct x from a short pathway in this tree. Why would I waste some precious nodes to readdress x somewhere else? I already have a pathway to x, and it's this pathway. You know, tack, 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 tack. This would be a pathway to reconstruct x. I'm not going to waste my nodes, basically. So I'm skipping it. I don't need it. However, when I find program 111 that halts, and which also outputs my desired string, 11011, well, the proxy for P of 11011 is now 2 to the minus 3 plus 2 to the minus 5 plus 2 to the minus 6. And therefore, if I write it in binary, why? Sorry?
The y of 5 is minus 3. Yeah?
Why 2 to the minus 3?
Ah, okay, it's the first one is minus 3.
The first one is minus 3.
Ah, okay.
Yes.
Okay.
2 to the minus 3 plus 2 to the minus 5 plus 2 to the minus 6.
Yeah, it's
So-
like plus.
If you were ready to code an algorithm, you would not compute them again from scratch. You would take, what's the latest proxy you had for that string, and you would add the latest contribution. And then you would realize, oh, my leading digit has changed. Therefore, I need to assign another node to that string. So I'm going to assign a non-trivial address. And this time, what happens when we do minus the log, well, ceiling of minus the log plus 1. I thought I would have done it before, but I guess we have to compute it. No, because it's a general idea that I need for later in the proof. So let me do it more generally than just for that case. I called it a fun fact because I was looking for names. Fun fact 1. Let alpha equals to 0.00001 and then b I plus 1, b I plus 2, which this is the ith bit. So it's only zeros. Eventually you get the first one at the ith position, this being the first, second, third, ith. Then you've got non-trivial bits. B is either 0 or 1. So that if you would write it in 2 to the minus something, it would be 2 to the minus I plus bi plus 1, 2 to the minus I plus 1 plus, and so on. Then, in this case, we have that alpha is an element of 2 to the minus I, strict inclusion, 2 to the minus I plus 1, soft inclusion. Okay, it's going to be some number between. This is a 1 and all of them are zeros. Or this is a 1. Okay? And because you have like non-trivial numbers here, and so they can approach as close as you want to this number being a 1. Which implies that log alpha is an element of, taking the log is a monotonic function, so I'm just going to be taking the log, I'm taking to the exponent, minus I comma minus I plus 1, and so minus log of alpha. Now I need to flip my domain. Well, flip my interval. However, this remains soft. So it's going to be I minus 1, comma, I, and this remains hard. I'm using the words hard and soft. I don't think it's a thing in English.
It's not, but I understood.
Yeah.
Yeah.
Strict inclusion, and what's the other one?
Open and closed is what I would say.
Oh,
yeah.
Yeah, open, closed. Thank you.
Yeah.
Same in French. We don't say soft and hard. All right. You know, these kind of things, these are fun facts. They're details. They're a bit annoying, but we got to do them to get the proof right. And instead of doing them in this awkward setting, I do them once and for all generically. All this to say that then we can take ceiling of minus log of alpha. And so I have a number which is strictly larger than I minus 1 and is potentially included at value I. So the ceiling is equal to I. Therefore, that expression that always comes and we see, you know, ceiling minus log of something, it does mean the position of the leading 1 in binary expansion. Right, I have alpha, the position of its leading 1 is I, by construction of the way I defined alpha generically. And if we take minus the log of alpha and then we take the ceiling, we get I. I can safely come back to my example now, but we haven't worked for nothing because we've got the general case later. All this to say that minus log of sx5, taking the ceiling, then I'll need to do a plus 1, because I will want to take a node at depth this plus 1. Well, I just have to look at where's the first bit, the first one. It's at position 3. So this quantity is 3 by fun fact number 1. Plus 1, it's 4.
So A is 0, 0, 1, 0.
Yes. Zero, I need to take the lexicographically first. So I'm going to walk along the 0 path as much as I can. 0, 0 I cannot do 0, 0. I cannot do 0, 1. It's already taken. So I'm going to do 0, 0, 1, 0. And this is going to be a new code word or a new node that I associate with the string 1, 1, 0, 1, 1. So I said, you know, in the case where we had 2 to the minus 6, I said I don't want to waste precious code words. I already have some assignment for 1, 1, 0, 1, 1. Because depth 6 was anyways longer. But now I have something that is shorter. I will take it when it's shorter. That's why we will re-update, we will give a new address once we found a better leading digit in the lower semi-computation of P of X.
Does that mean that you free that node that you allocated before or not?
No,
That
I
node
leave them
was still
there.
taken.
Yeah, yeah. We could try and be more economical by, you know, dynamically rechanging, but it's annoying that we created new space. Now the lexicographic ordering would be messy. It'd be more complicated. We don't need to. Okay. Suppose that actually P of 11011 is equal to 0.001101. I don't know, I made it up. I make everything up in this example. Anyways, but suppose that the real universal probability of the string x that we're considering has a leading bit at position 3. And then it has other bits. Right? We know that this quantity will always be smaller than that. But eventually it will stabilize the leading bit. In my example, it's already done. After 5 programs that have halted, it has stabilized the value of the first bit. Well then, the lower semi-computation of, suppose that actually this, I'm just going to say it because I'm going to want to write the generic case. Then the lower semi-computation of S of 11011 will keep on going forever, but I will never allocate any more nodes. I will always be in the case where I allocate the empty set. Because I'll get another halting program for the string 11011, but it's going to be ridiculously long program, so it's not going to contribute anymore to the changing digit of the proxy. Right? And we know that this will always happen at some point. So yeah, in this case, in my example, we're sort of done. We're going to get many more programs with that output, but we're not going to assign any shorter nodes or addresses for nodes. Questions? Okay. Eventually, there will be a program PL. So I'm going back to the generic case. There will be a program PL that computes X. So if it computes X, XL is equal to X, right? XL is the output of the program PL, according to our definitions of the quadruples, so you can think of that. and whose contribution to Sx will make the leading one in the binary expansion of Sx to be at the same position as the leading one in P of x. This is guaranteed because Sx is a lower semi-computation of P of x. So eventually it will stabilize the leading one. This will give a first. Oh yeah, in our example, this PL was P5. You know, it was this one who stabilized for the first time the leading bit in P of x. And for the last time. So this will give a first and only node at depth no, can't do that here. Minus log s of xl ceiling plus 1, which is equal to ceiling minus log p of x plus 1. Why is now this quantity the same as that quantity? Well, you can see it from this, the fun fact number 1. We saw that if we have a number whose leading bit is I, whichever is the rest, well, ceiling of minus log alpha will be I. And so here by assumption we have that this and this have the same leading bit. So they have the same quantity, ceiling minus log. And obviously plus 1. Plus 1 doesn't change it. So we're sort of like, we're in that scenario where we have this and this. Okay, so there will be a first and only node at depth, this, to which the string xl equals x will be allocated. the address of this node is AL. AL. Obviously, I'm just carrying, you know, we have a PL that has halted. So according to our nomenclature, we have XL, we have S of XL, and we have AL. And in our example, AL was this, 0, 0, 1, 0. But what matters is going to be the length of AL. Well, length of AL is this. So it's this. Minus log P of X plus 1. Right? It's the length of AL is what I also have called the depth. Here. Are there questions? Good. Now, we're not really done. We sort of have a big construction. We're allocating nodes for all strings. Even if what I'm after is computing this one, I don't mind. I'm allocating nodes for all strings. In fact, look at T. T has so far no input. It's running all programs. It's printing out quadruples. I have not yet told you what T is going to do on what input. But maybe you have an idea.
The P, the binary expansion of P, since we're assuming like our criterion for stopping this is when the first bit, the leading one of P is stabilized. So just to know what P is.
It doesn't need to know what P is.
It's enough to know the address in the tree, which is the A.
Exactly. If I want T to produce X on the shortest possible way, I'm just gonna give him AL, which is the shortest possible address for X. And so T is gonna go, it's gonna do its stuff. He's gonna allocate a ton of nodes. Most of them is not gonna be AL. Eventually he's gonna say, oh, I just wrote down some string on some node, and yeah, this pathway corresponds to AL. I halt and I output that. Oh yeah, sorry. Okay, yes, I'm switching my construction from my notes in case now some of you might be following them. So far, T has no input. And by the way, nothing will make it halt so far. It's just printing a list of quadruples. An input for T to produce X is AL, which T interprets as. Now you can imagine that I'm rewriting the last line of description of T right here. Okay, it's doing all of that, blah, 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 producing quadruples. And then last line of code would be output the string that is to be allocated on the node AL. Right, just as a reminder, AL is eventually there will be a program PL corresponds to that program PL. PL is the one that stabilizes the leading bit of P of X, and then we give AL. This will be the last time that we allocate an address for the string, and it will be the shortest one because by construction it will have one bit more than the position of the leading digit in P of X. And so we're going to say P, okay, do that for all strings, and output the string that is to be allocated on the node AL. In our example, it will output that string. I'm going to erase downstairs here. Okay. Thus, a program for you is to produce X is I bar AL. Where the Turing machine T has an ordering number Ti. So basically I bar is the program which gets me to that Turing machine. It's going to simulate whatever this one does. And the second entry is AL, the input of the Turing machine.
AL is the node that I want to pick out of this tree?
Yeah.
But what stops me from picking, for example, one of the previous ones that also gave the same X?
Oh, this would also be a program for X.
Yeah.
But this is longer.
Yeah.
In my example, it's a cartoon. It's only 2 bits longer. Who cares? But it could be many, 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 many bits longer. This is precisely, what's the length of this? 4 was ceiling of minus log P of X plus 1. Was it precisely that quantity?
Right. So if I'm trying to get to the Kolmogorov complexity of X, it seems like I have to pick the last one.
Yeah.
Not one of the earlier ones.
Exactly.
But how do I know? A is supposed to be an input, right? So how do I know ahead of time this node is supposed to be the last one that stabilizes the first?
You don't know, but you don't need to know. Now, the program here, in the case of our example, is dovetail all programs, do these things with quadruples, and stop once you have allocated a string to the node number 0010. Okay, chef, let me start. Blah, blah, blah. I dovetail all programs. I got P1. I'm happy. Oh, no, I'm not really happy. It's useless. It's not producing the string I want. Blah, blah, blah. I keep going. P2. Oh, cool. P2. I'm starting to lower semi-compute this. Actually, no, sorry. He doesn't even know X. Doesn't even know X. We know X. So I was putting emphasis on those ones because we know X. But my program only knows this address. So it's allocating that address. No, that's not the address I'm looking for. Then it's allocating that address. No, it's not what I'm looking for. And it's allocating no address. And then, whoa, I've got it. So it will have the So at this point, a Turing machine on input 0, 0, 1, 0 sorts of singles out this last quadruple and say, okay, what I want to produce is that string.
Yeah, I'm still confused. My question is, how do I know I'm supposed to input that node of the tree?
Ah.
And you've told me ahead of time that that's the last one that will stabilize that bit of pvex, which is all fine. But how am I supposed to know that node ahead of time?
Okay.
But you're just showing that you can build a program that computes X, right?
Who said you need to know?
You don't need to know, you just want to show that it's existent to have one program that produces X. So if you can enumerate it, you can.
We're proving this. Ignore y. I want to show that the shortest program for x has length smaller than this quantity. So I'm going to come up with one program which produces x and which has length this quantity. I don't ask you to come up with it generally for all x. I'm just saying it exists. And that program is this, basically. This which tells me simulate the Turing machine T, and this which tells me on input AL. The length of this is precisely that quantity. Therefore, we found one program of that length which computes x from y, and so the shortest program has a shorter length. Because the question you ask, you seem to be asking too much. Like, you could also say, oh, consider x star. How do I know it's x star? You know, what we want to do here is to come up with some program of that length, which computes x from y. And yeah, that's it. It has length. Well, the length of AL, I've wrote it somewhere, right? Yeah, the length of AL is here. The length of that is, this is a constant independent of x. I simulate only once that Turing machine T on that input. So it has length of AL, whoops, plus O of 1, which is equal to minus log P of x plus O of 1. It's time. I'm happy I muscled it through. If you carefully read it, you might be bugged by two subtleties. One of them is, what guarantees us that there's going to be enough space in this tree to keep allocating nodes? And this is going to explain the +1. By going just one bit further, we're making sure we have enough space in the prefix tree. That's one thing. The other part which might be bugging you is, we've constructed a Turing machine T, which has a set of input which leads to a valid computation. By construction, the set of valid computations is the set of addresses, is a prefix-free set. Good luck, Will, for your exam.
Thanks.
Buona fortuna. And so the set of valid A's that lead to a T, a Haugen computation for T, is a prefix-free set. But how can we make that self-delimiting? We saw the other way around. When we have a self-delimiting Turing machine, we know that it will have as a consequence that the set of its valid computation is a prefix-free set. Now what we've done is the other way around. We have a set of inputs for T, which leads to some output. That is a prefix-free set, because they correspond to the node on the prefix tree. Yet, how can I make T a self-delimiting Turing machine? Because once I ask you to produce the string via simulating T, it was simulating all Turing machines that were of the form self-delimiting Turing machines. But both of these problems are fine, after all. I'm basically putting problems for you to be critical about. And at least by not getting stuck in these problems as we did this proof, I managed to finish it, which is the first step. And then next time, either I'll address these problems or I'll address something else, depending on the inspiration for the last course. That's it for today. See you next Tuesday, and hopefully for this social event that we do after also. Have a nice week.